Looking at chapter 25, we're looking at alpha, beta, and gamma radiation. And there are 3 different modes of radioactive decay that's described in our handout, so make sure that you read through this. But in the meantime, we're going to get started on the homework questions. Let's look at number 1. The biggest thing to make sure that you are aware of when we are doing practice problems looking at nuclear equations is that the sum of the mass numbers of the product has got to equal the sum of the mass numbers of our reactants. Or reactants and products need to be equal. Let's see what we've got. We've got neon, and again, remember, the top is our mass number, the bottom's our atomic number. We can see that this is a positron emission. So I must have 9 down here for the atomic number plus 1 to equal 10. So my number of protons must be 9. So we need to see what atomic number is 9, and that's fluorine. So I can give it its symbol F. And then to find its mass number, remember our beta particles have no mass, so it must be equal to 19. Looking at number 2, we can see that it is a beta emission. So if I have a -1 here, 27 minus 1 would equal 26. So we must have an atomic number of 27 down here, and on our periodic table we can see that that's cobalt. And then again, it must be the same mass as this iron mass. Third one is the same, another beta. So to have 19 protons on the left, I must have a 20 right here, which is calcium. 20 minus 1 is 19. And it must have an atomic mass of 40. So that's calcium. Our next 2 are electron captures. So if I look at, I've got argon with a mass of 37, atomic number 18. So 18 minus 1 would be 17. And then looking at your periodic table, atomic number 17 is chlorine. And it must be the same mass as argon because, again, electrons do not have the mass. Iron, going through electron capture, 26 minus 1 would be 25, which is manganese. Same mass as 55. Here I'm showing a transfer of aluminum to magnesium. So what must this other product be? Well, I have to, again, remember my bottom numbers and top numbers, my mass has to equal. I can't create or destroy. So I must have 1 proton, right? 12 plus 1 would be 13. And I must have 25 plus 1 would be 26. So I've got to have hydrogen with a mass of 1, and there's 1 proton. So it's just a hydrogen. Over here, we can see that I had a helium as a product, as my alpha particle, and that's shown as 4/2, so 2 protons, 2 neutrons for a total mass of 4. So 3 plus 2 is equal to 5, so 4, there must be a 1, and we know atomic number 1 is hydrogen, and then let's check our mass. 6 plus 4 is 10, so 9, the top number must be a 1, so we have another hydrogen there. Here we've got a neutron. And a neutron, remember, neutrons do not have a proton, but neutrons have a mass of 1. That's why it's written as a 1/0, 0 meaning no protons. So on the right side, I've got 11 plus 2, 13. So my question mark must be 13, which is aluminum. And then let's check our mass, 24, 25, 26, 27, 28. So this must be 27. Because neutron has a mass of 1. 27 plus 1 is 28. All right, on this side, I've got 19 plus 1 is 20. So since I already have a 20, I can't have my electron capture. I can't have a beta emission. I got to have a 0 on the bottom in order to have my left side equal my right side. And a 0 on the bottom must be a neutron. And then if we double check, 40 plus 1 is 41. So 40, the top number must be a 1. Yep, it's a neutron. On this guy, I've got 95, 96, 97. And on the right, I have 97. So again, my bottom number must be a 0. And my top number, 241, plus 4 is 245. And that's 243. So I need 2 neutrons. That would give me 43, 44, and then a second one would be 45. So 2 neutrons. For E, we can see that I've got 96 plus 6, 102. So on the right, I need to have 102 for my number of protons, my atomic number, which is NO. Now let's get our mass to equal. So 246, which would be plus 12, is 258. And again, there's 4 neutrons. So 258 minus 4 would be 254. And the last one for number 1, to figure out what's missing, I'm going to look at what I have on the right. I have 100 plus 0 for my protons. So 92 plus 8 must be my missing number of protons for the bottom number. 8 we know is oxygen. Now let's find out our mass number. 249 plus 5 neutrons. So 5 times 1 is 5. 249 plus 5 would be 254. 254 minus 238 would give me a mass of 16. So that must be oxygen because of the number of protons, 8. Okay, which of the following nuclear decay by this beta decay? Now, beta emission, this is something you need to know, has a high neutron to proton ratio. Okay, so I'm going to show this H3. 3 is the mass. So I'm going to show how many neutrons and how many protons that is, this 2 over 1. If it has a mass of 3 and it's hydrogen, hydrogen has 1 proton, and 1 plus 2 would be 3. So neutrons over protons, 2 to 1 ratio. Compared to oxygen, 16. Well, oxygen's atomic number is 8. So that must be 8 protons, 8 neutrons. That's only a 1 to 1 ratio. If we look at fluorine, 20, and we know fluorine has an atomic number of 9, so there'd be 11 neutrons, 9 protons. And nitrogen has an atomic number of 7, so that would be 6 neutrons to 7 protons. So we can see that fluorine, this 11 neutrons to 9 protons, is a much higher ratio than a 1 to 1, or this is even less than a 1 to 1. For part B, this one, notice the difference. This is a beta particle 0 plus 1 compared to a 0 minus 1. This 0 plus 1 is a positron emission, and that would be a low neutron to proton ratio. So if I looked at my uranium and its protons are 92, and then I subtracted the mass minus 92, I'd get the number of neutrons. And same for fluorine, sodium, and sodium. So to look at a low ratio, we could see our lowest ratio would be this sodium, 11 over 11. All right, again, looking at our beta decay, so we want a high ratio. Our high ratio would be this phosphorus. And again, in order to find that out, I had to figure out how many neutrons and how many protons each one of these had. For part B, again, similar to here, we want our low neutron to proton ratio. And looking at my lowest ratio, looks to be this potassium, which is a 1 over 1 essentially. Looking at number 3, when we have the nucleotide thallium-206, so I looked up thallium's atomic number is 81, and again, mass up here is 206. It decays to lead-206, so Pb is lead-206, and looking at the periodic table, lead's atomic number is 82. So the mass is staying the same, so that means our other product can't be anything that has mass to have our mass equivalent. So it's got to either be an electron or our beta emission, because also going from thallium to lead, notice that I either need an electron, because 82 minus 1 would be 81, or I need that beta emission, because again, 82 minus 1 is 81. So it's either of those two. Number 4, we need to know, and actually for the rest of these problems, we need to know a few different equations. To find out how much mass remains when we're looking at half-life, we're going to use this 1 over 2 to the nth power times the original mass. And the nth power is how many half-lives have passed. And we find that by taking how many days or how many seconds or how much time has passed divided by how much time it takes for the half-life. And you would be told that in the problem. So, for example, this one tells us that Iodine 131 is administered orally in the form of NaI as a treatment for thyroid cancer. The half-life for iodine is 8.04 days. If you began with 48.3 milligrams of this isotope, what mass remains after 18.3 days have passed? So what's nice is that we have days and days, so we don't have to do any unit conversions. So I can say that 18.3 days have passed, and 8.04 days is how long one half-life is. So if I did 18.3 divided by 8.04, that's 2.3 half-lives. Then I can just take that n and I can plug it into this equation. This equation can be rearranged or also written as 1/2 to the nth power or 1/2 to the nth power. Either way, you get the same answer. So I'm going to take that original mass, that 48.3 milligrams, and 1/2 to the 2.3 power. So I would do this in my calculator first. If you don't have a scientific calculator, do 2 raised to the 2.3 power, then do 1 divided by that answer, and then times that by 48.3. You should get 9.8 milligrams. For this guy, radioactive isotope mercury 197, it's used in medical imaging. If we have 67.1 milligrams of mercury administered to a patient, how many milligrams are left in the body after 192.3 hours? I have 192.3 hours, and if I look at the table that's above, which is on the other sheet, I've got mercury 197, and its half-life is 64.1 hours. So I'm going to go back to my equation here. So I got my total amount of time over the half-life, which is 3. So that's how many half-lives have passed. So then I can just plug it into that equation, 1/2 to the third times 67.1, and I would have 8.31 milligrams left in the body after 192.3 hours. The radioactive isotope thallium-201 is used in medical imaging as indicated on the table above. In addition to gamma radiation, what is the mode of decay for thallium-201? And if we look at this table right here, this thallium, it tells us the mode of decay is EC, which is electron capture, and gamma radiation, just listed right there in the table. The next one, it says, when the nucleotide thallium-201 decays this way. Okay, so if I have thallium, mass number 201, if I look at my periodic table, its atomic number is 81. So I write this as 201/81 thallium. Okay, so that's my starting point. Now, if I have electron capture, so I'm going to show that I have my electron with no mass and electrons of -1. That means that my product, again, my mass has to equal, is 201 with the mass number. My atomic number, 81 minus 1, has got to be 80. So my product nucleotide is going to be mercury 201. Number 7, copper acetate containing copper with a mass of 64 is used to study brain tumors. This isotope has a half-life of 12.7 hours. If you began with 25 micrograms of copper 64, what mass in micrograms remains after 63.5 hours? So I found my n, my number of half-lives first. So 63.5 hours divided by 12.7 hours is 5 half-lives. And then I can plug it into my equation. So 1/2 to the 5th power, or 1/2 to the 5th power, times that by 25, which was my original amount, micrograms. And I got 0.781 micrograms remaining. Number 8 is set up very similar. We've got gold 198 used in the diagnosis of liver problems. The half-life of gold 198 is 2.69 days. If I began with 2.8 micrograms of this gold isotope, what mass remains after 10.8 days? So I figured out how many half-lives that was, which is 4. And then I did 1/2 to the 4th, or 1/2 to the 4th power, times my original amount, and I got 0.18 micrograms. And lastly, we're told that we have iodine 131 is used to treat thyroid cancer, and it decays by beta particle emission. I've got my iodine 131. I looked at the periodic table, and its atomic number is 53. It decays by beta particle emission, so that's a product. My other product must be 54, because 54 minus 1 is 53. Remember, everything needs to match left and right. And my mass, obviously the beta emission does not have any mass, so my mass is 131, so I have xenon 131. I figured out how many half-lives I had. I took my 40.2 days divided by 8.04 days, which was the half-life, which is 5. I took my original amount, 2.4 micrograms, and then 1 over 2 to the fifth, and I got 0.075 micrograms of iodine 131 remaining.